Hello, thanks for joining me. My name is Shachar, and I'm from Yaron Bromberg's Complex Photonic Group at the Hebrew University of Jerusalem in Israel, where we study complex systems with light. I'll be talking today about null fiber apparatus we developed for wavefront shaping in multimode fibers, which works by controlling the transmission matrix. Then, I will show how we use the same system for image reconstructions for multimode fibers. We collaborated in both of these works with Sebastian Popov from Institut Langevin in Paris. Before that, I'd like to thank the organizers for giving me the opportunity to present our work and apologize for pre-recording this talk. I'd be happy to answer any questions. Please send them to my email. It appears here. I'll start with explaining the novelty of our experimental setup, and then that will lead me to both applications. So first, let me present the main feature of our setup. The principle is utilizing specular sensitivity mechanical perturbations. We have an array of piezoelectric plate benders, which are placed above a multimode fiber. By controlling the height of these actuators, we control the curvature of the bend they apply. The bend changes the phase that is accumulated between modes and thus changes the speckle pattern we observe at the distal end. Like in the schematics, 3 different geometries lead to 3 different speckle patterns at the distal end of the fiber. So bends actually change the transmission matrix of the fiber. In wavefront shaping, one usually wants to achieve control over the electric field after it propagates through a scattering media, like a diffuser, milk, or even a cell culture. Say you initially have a plane wave, like demonstrated here. Due to multiple scatterings, the transmitted wavefront will no longer be a plane wave, but rather a speckle pattern. In the past decade, many groups have shown how to tailor the incident light to correct for the effect of scattering, so that you achieve a desired output. In this figure alone from Velakup and Mosk's pioneering work that was published in 2007, the desired output is a focus. The main difference is that our approach is rather than shaping the incident wavefront, we shape the medium itself. This has a few inherent advantages, like an increase in the number of degrees of control and possibility of controlling multiple wavelengths simultaneously. So one of the first tasks that is performed with wavefront shaping techniques is focusing. On the top, you can see the full experimental setup we used. We used an optimization algorithm to adjust the bend configuration, and were able to focus most of the energy to a chosen speckle grain. Here you see an example to the speckle pattern before and after the optimization. This is the first experimental demonstration, as far as we know, of such a method for wavefront shaping. We also showed that the increase of enhancement depends on the number of actuators, like we see in this graph here. We use an increasing number of actuators and saw an increase in the enhancement, which we define as the intensity of the speckle relative to the average intensity. Then we wanted to test how well this works in FiO mode fibers, which have recently been considered for spatial division multiplexing in optical fiber communications. So we switched the FiO mode regime to a fiber that supports a small number of modes in interpolarization, and saw that we were able to convert between fiber modes. For a given input beam, we were able to shift the energy from one polarization to another, and also to change the spatial mode we observe at the distal end of the fiber. We also looked into the rate at which our setup can be operated. In principle, the modulation rate is limited by the response time to mechanical perturbations, which we measured at about 30 milliseconds, corresponding to a modulation rate of 30 Hertz. Now, I'm moving to the second part of the talk. The idea of combining machine learning and specifically neural networks to study complex systems has been laid for a few decades now. However, it wasn't until quite recently that the huge potential of the combination of the 2 domains was really demonstrated. Specifically, I'd like to note the works of the teams of Psaltis and Mossel from EPFL, Lei Tian's group from Boston University, and Lei Su's group from Queen Mary University of London. Typically, images such as handwritten digits are displayed on a DMD, from which they are projected on the input facet of the fiber. The intensity of the speckle is recorded at the output, and then a trained neural network is used to reconstruct the input images. The problem is that the input-output relations in multimode fibers are very sensitive to perturbations. If the fiber shifts a little, then a network needs to be retrained. This is probably why most previous works focused on a single fiber configuration. In Queen Mary University, however, they extended this and trained the neural network on speckle from a fiber which was perturbed by continuously moving a steel bar along a segment of 3 centimeters. Being so sensitive to perturbations limits the possible applications of such models, because, for example, for endoscopy, we'd need to be robust for fiber configurations and bends that we have not previously seen. or learned. This is where we fit in the picture, as with our setup, it is quite easy to generate bends. We can train a network on hundreds of fibers configurations, which hopefully make it more resilient to perturbations. So what we do is quite simple. We display images on the DMD, project it into the fiber, record the intensity of the speckle pattern at the distal end of the fiber, and get a speckle digit pair. We collect hundreds of thousands of such pairs for different digit images, like a few you can see here on the left, and for different fiber configurations, which we create by applying different positions on the actuators. We use some of these pairs to train a neural network and others, which originate from different input images and different configurations, to test the fidelity of the reconstruction we get. We don't give the network any indication as to the configurations the speckle originated from. At this point, I should also refer to how different the speckle from different configurations are. We found that two random configurations have an average Pearson correlation of 12%, which is quite low and actually comparable with the macro bends we tried. So we believe that using our setup, we actually get bends that mimic those achieved in real-life scenarios, such as in endoscopy. We started by training the network on a single configuration of the fiber. That is, we define a random set of positions for the actuators and acquire image pairs only from this configuration. To avoid confusion, perhaps I should clarify that even though experimentally the input is a digit image on the DMD and the output is a speckle pattern, when we refer to the neural network, it's also reversed. The input we give the network is a speckle, and we train it to predict the digit image. On the top of the slide, you can see the schematics of the experimental setup. We are now using a step index fiber with a 50 micron core, which supports around 500 modes for each polarization. When training is complete, we test it by reconstructing unknown speckle and compare its prediction with the actual input, which was displayed on the DMD, which we referred here as the ground truth. You can see a few examples for our results. Qualitatively, you can see that the reconstructions are extremely similar to the ground truth. Qualitatively, the pixel-wise accuracy here in orange and the Shachar index here in blue are calculated. We find the accuracy at 97%, and the Shachar index, which is the intersection of a union score of the binary patterns, is 0.84 out of 1, which is very high. We then train another neural network, this time on 8 different fiber configurations with an average Pearson correlation of 14% between one another. I remind you that the network has no indication to the originating configuration. In the bottom figure here, you can see representative examples for reconstructions from 2 of these 8 configurations. The reconstruction is still excellent, though subtle differences from the ground truth can be noticed by a meticulous observer. The accuracy and Shachar index reflect this, and you can see that they are slightly lower. To see how small perturbations affect the CNN's performance, we started from a random fiber configuration, then performed 300 steps, where in each step, we changed the curve created by one of the actuators and acquired the image pairs from that configuration. So we have a data from 300 configurations. In the left figure here, you can see the Pearson correlation of these steps. The y-axis denotes the correlation coefficient, and the x-axis is the step index. The blue curve shows the correlation of each step with the original random configuration. The purple one shows the correlation between 2 adjacent steps, and you can see that it varies from a little over 70% to 100%, which is because the actuators have different effects on the correlation. We then let the network train on 5 out of every 10 of them, so on 150 configurations in total. In the right figure here, you can see the representative examples for the reconstruction of 2 steps. The upper one belongs to a step that the model trained on, though still the reconstructions is of unfamiliar patterns. And the bottom one is of unknown configuration. The middle row is again the ground truth to which you should compare. We again see that the reconstructions are very good, though the Shachar index is a little lower. This decrease is because we took much less data from each configuration. Interestingly, we get very similar reconstructions for both the familiar and unfamiliar configurations, which means that the model overcomes the changes to the speckle in the unknown perturbations, making it resilient to small perturbations, which is quite cool. Okay, so last, we wish to test if we can train the CNN to be resilient also to large perturbations. For that, we acquired training and testing data from 943 random fiber configurations and testing data from additional 800 configurations. The average percent correlation between all these configurations is again 12%. Because of COVID-19, we do that over a few months, so we also account for changes to the setup due to environmental changes. Once training is complete, we test the model on unknown speckle patterns from known configurations and look at the reconstructions it creates, like you see in the left 3 columns. The fidelity is not as good as before, but the digits can, for the most part, still be recognized, and most predictions are similar to the ground truth. Then we test it over unknown patterns from unknown configurations and see similar reconstructions. While not perfect, this is exciting. Our quite humble neural network is robust against mechanical perturbations that were applied randomly on a multimode fiber. This is the first time to our knowledge that bend resilience is being demonstrated to such an extent. Okay, so it's time to sum up. I presented you with a system that utilizes fiber bends. Instead of suffering from the effects of mode mixing and coupling, we look at them as a positive thing and are able to turn this nuisance into a nice feature. I then showed you 2 rather common wavefront shaping experiments that we are able to reproduce with this technique, namely focusing in multimode fibers and mode conversion in FiO mode fibers. Then we changed directions and saw an application for bioimaging by combining our setup with deep learning. We saw that by training a neural network on speckles that are generated from hundreds of different and low correlated fiber bends, we can later achieve bend robustness and provide reconstructions even for unknown input patterns from known bends. Inter-process synthesis, we also reproduced results that were achieved in the last few years by other great research groups and saw that our setup overcomes small perturbations to provide high fidelity reconstructions. This method is obviously not perfect. Its main limitation is that the training is sensitive to the domain of the images. This means that if I give it a speckle pattern that corresponds to, say, an image of a house on the DMD, rather than a digit, it won't be able to reconstruct the image well, because new DMD input is from a different image domain. However, this does not affect possible implications for medical imaging, as we can acquire data that belongs for the same domain, and since we see that our system is stable enough to be used over months with the same data, this would not require the expensive and time-consuming action of retraining a neural network. With that note, my talk comes to an end. Thank you very much for listening. I hope you enjoyed this session and will continue to enjoy the rest of the conference. Here's my email again. In case you have any questions or comments, I'd be more than happy to address them.